Swayam Prabha. Digital India. Educated India.
Hello viewers, welcome to lesson 2 of module 5. Module 5 is on payment evaluation and rehabilitation. In the previous lesson, that was lesson 5.1, we discussed about the need for rehabilitation and various techniques that can be adopted for functional and structural evaluation of payments. In this lesson, we will be discussing about designing overlays for existing payments using Indian Roads Congress method, that is IRC 81 1997 version. The specific objectives of this instruction will be, after completing this lesson, it is expected that the student would be familiar with the background for the IRC method of overlay design. It is also expected that the student would understand the standard procedure to be adopted for conducting structural evaluation of payments using Benkelman beam, because IRC 81 1997 version is based on the structural evaluation of payments using Benkelman beam evaluation technique. It is also expected that students would be able to carry out overlay designs for flexible payments on the basis of Benkelman beam evaluation. We have briefly discussed about the need for evaluating payments in the previous lesson, lesson 5.1. We know that once constructed, payments gradually deteriorate in terms of its functionality and also in terms of its structural condition. The structural strength also gets reduced. There will be cracks that would be forming, there will be form deformation, there will be deterioration of materials in various forms, resulting into reduced structural soundness of the structure. Also, the functional performance also gets deteriorated because of the surface distresses. So, the riding comfort, safety and other aspects that are important to the road users will also be affected. Thereby, the functional performance gets reduced, simultaneously the structural performance also gets reduced. We are concerned about these two aspects. So, to improve the structural condition, what needs to be done, how to assess the requirement, how to assess the present condition, this is what we are going to discuss. This discussion will be based on the guidelines that are provided in the Indian Roads Congress guidelines. So, as just mentioned, payments deteriorate functionally and structurally with time. This is because of application of traffic loads and also due to the action of different climatic factors, action of moisture, action of temperature and other parameters. It is necessary to evaluate the condition of the existing payment in terms of its functional and or structural condition periodically. Some agencies carry out only the functional evaluation, some agencies carry out only the structural evaluation, but there are agencies which carry out both the functional evaluation and structural evaluation and evaluate the payment in terms of its capability to provide proper functional performance and also proper structural performance. The evaluation will enable the timely assessment of the condition of the payment at any given point of time. What is the condition of the payment in terms of its functional performance, in terms of its structural performance, and on that basis one would be able to assess what is the requirement if any, and what is to be done to improve the condition of the payment. Overlay is that reinforcing layer that we provide over an existing payment. That is because payments that do not have adequate structural strength to carry the projected future traffic will have to be reinforced by providing additional payment layer. Normally, there will be situations where we are trying to assess a given facility in terms of its ability to carry traffic satisfactorily or to serve satisfactorily for the next 5 years, 10 years, 15 years period. So, if we can take into account all the traffic that has to be served over the next 10 years period, if 10 years is the design life period. So, we have to make an assessment of whether the existing payment is capable of, in terms of its structural strength that it has got at the present, whether it is capable of serving the projected traffic that is going to be there over the next 10 years satisfactorily. The payments that do not have adequate structural strength will have to be reinforced by providing additional payment layers. As you can see from the in this diagram, so we have an existing payment placed over a subgrade of given strength. This is the existing, say it consists of 2 layers, it can be 3 layers or 4 layers also. So, if you can assess what is the strength of these 2 layers placed over the subgrade, then we can assess if we have a criteria which tells us what is the strength that is required to carry a given number of traffic loads satisfactorily. Important thing is we need to have a criteria which will tell us whether the given strength, existing strength is adequate or not, and if it has to carry more traffic, what should be the initial strength. That criteria is very important. So, we need to have a performance criteria which correlates the initial strength in terms of the parameters that we are using to evaluate the existing strength and its ability to carry further traffic. So, once we are able to assess the condition of the existing payment and also in terms of the subgrade strength, we can, using the criteria, we can assess whether this payment is capable of carrying more loads or not. We can also assess how many more loads it can carry, that is what we call as remaining life. What is the remaining life of the payment we can assess. On that basis, we can say what is the requirement for additional reinforcing layer. That is what is depicted here. So, in this case, the need for reinforcing was felt. So, the overlay that is provided is depicted here. The guidelines that we are going to discuss here are as per Indian Roads Congress 81 and its 1997 version. These are guidelines for strengthening of flexible road payments using Benkelman beam deflection technique. This is the title of the guidelines. Guidelines for strengthening of flexible road payments. We are referring to flexible roads, flexible payments, and these guidelines are meant for Benkelman beam deflection technique. The first version was in 1981 and the first revision is what we are discussing, it is 1997 revision. These guidelines are based extensively on the basis of the findings of an MORTH, Ministry of Road Transport and Highways, Government of India, sponsored research project. It has got the code R6, which was entitled Development of Methods such as Benkelman beam deflection method for evaluation of structural capacity of existing payments and also for strengthening of any weak payment. This was the main objective of the research scheme. It was to develop Benkelman beam and other related similar methods for evaluation of structural capacity of existing payments. So, methodology for evaluation of structural capacity of in-service payments and also for finding out the strengthening requirement of any weak payments. The scope of these guidelines are, these are meant for evaluation of the strengthening requirement of existing flexible road payments using Benkelman beam technique. So, this is meant for flexible road payments and is also meant for technique Benkelman beam payment evaluation technique. The payment performance is closely related to the elastic deflection. It is believed that payment performance is closely related to the elastic deflection that the payment undergoes when it is subjected to a standard load. Elastic deformation under standard loading conditions depends on various parameters such as the condition of the subgrade, its moisture content, degree of compaction, and the condition of various other layers including granular layers, bituminous layers, and also it depends upon various climatic conditions like temperature, provision of drainage, thickness of various layers, quality of different materials. So, all the pavement related parameters affect the elastic deformation of a pavement when it is subjected to wheel loads. Winkleman beam is a very simple apparatus and it is commonly used for measuring the surface deflection of a pavement under standard loading conditions. A schematic arrangement of the Winkleman beam is shown here. This is the Winkleman beam. It is cut into cut at several places because its full length cannot be shown in sketch. This is the probe point which would be resting on the pavement surface at a point at which we are trying to measure the deflection. As you can see here, since it is very long, so its extended portion is connected here by nuts and bolts. So, it can be dismantled and then for ease of carrying and then conveyance, it can be carried in two different parts, but when we actually use it for deflection measurement, we connect them together. So, the full length of the beam is going to be attained. The full length of the beam, the practical length of the beam that we are going to utilize is 2.44 plus 1.22, that is 3.66 meters. As you can see here, from the probe point, as I said, that is the point at which we are going to measure the deflection of the pavement, to a hinge. So, the beam is hinged here and this is where we are measuring the deflection. We are using a dial gauge here. So, the movement of this end of this beam is measured with the help of this dial gauge. The probe of this dial gauge will be resting over the beam. So, as the beam moves up and down with reference to the upward and downward movement of the probe which is placed on the pavement surface, as the pavement surface deflects and rebounds. So, the probe points also goes down and goes up. The corresponding point, end point also will go up and go down. That can be recorded with the help of this dial gauge which is positioned here. So, what we are basically interested in the movement of this beam, rather the movement of the end points pivoted, and while the beam is pivoted about this hinge. As you can see, the distance from the probe point to the hinge is 2.44 meters and from the hinge to the point at which we are measuring the deflection is about 1.22 meters. You can see the ratio is 2:1. Therefore, if the actual deflection of the pavement or actual movement of the probe is say about 2 millimeters, the deflection that would be measured by the dial gauge will be 1 millimeter. So, this beam is supported by a support frame and with one rear leg, there is one leg here and there are two front legs here. So, with the help of these three legs, the support frame will be supported and the beam will be supported with the help of this arrangement here, and it is hinged about this location. In its normal condition, during transport, it will be connected to the main supporting frame with the help of a connecting pin here. but when we are going to measure the deflections, we will remove this pin and allow this probe to rest on the pavement surface, so that it can be freely be rotating about this hinge point. So, what we basically have here is 3 supporting legs, 1 supporting frame which supports the beam about this hinge point, and the beam will rotate about this hinge. So, as the pavement goes up and down at the probe point, the corresponding end point will also move accordingly, which can be recorded using the dial gauge. The principle is illustrated here. It is a very slender beam, very narrow beam, and total length, as I mentioned, is 3.66 meters. It is hinged at a distance of 2.44 from the pivot end. So, initially what is done is a load is applied here, and in its deflected condition the probe point of the beam rests on the pavement surface. This is the corresponding position of the end of the beam, which is rotating about this hinge. So, this deflection can be observed, this portion of the beam can be observed using a dial gauge, and when this load is removed, this pavement surface rebounds, and this would be position of the beam corresponding to the rebounded portion of the pavement surface. So, the end point will come down. This position will be recorded using the dial gauge. So, observed difference gives us an indication of what is the rebound deflection of the pavement. Using a Winkleman beam for measuring the deflections, the load that is applied is either static or creep loading. As we just discussed, Winkleman beam is an apparatus used for measuring the surface deflection of the pavement subjected to standard truck load. What is important here is we are using load that is very similar to the load that is being applied on actual pavement surfaces. Although we are standardizing the load, we are not going to apply any amount of any magnitude of load that is going to be there on the pavement surface. We are going to standardize this load, how much load has to be applied, that is a standard load, but it is applied through a truck. As you can see here, what we are going to measure here is either the maximum deflection when the load is applied or the maximum rebound deflection when the load is removed. So, maximum surface deflection is measured using Winkleman beam in 2 different modes. As per a washout procedure, Western American State Highway officials method, the deflection noted as the wheel load approaches the point. So, the probe is kept on the pavement surface, wheel load gradually approaches the point. So, when the wheel load is directly above the point, we see the maximum deflection, that deflection is observed. That is what is observed in the case of a washout procedure. But if you are adopting Canadian Good Roads Association CGRA procedure, the method of observing the deflection is slightly different. What we do here is we observe the rebound deflection, and it is measured as the load is removed from the point. Initially the pavement will be subjected to the load, then we know what is the reading corresponding to the deflected position of the load. When the load is removed away from the point, the pavement rebounds, we see the reading again, and the difference should give us the rebound deflection. So, that is what we measure in the case of CGRA design evaluation procedure. The washout method of measuring deflection using a Winkleman beam is depicted here. In this case, initially the load is away, the probe point of the beam is kept here. So, we measure the corresponding deflection. So, as the wheel load gradually moves forward and is directly above the point, that is when we are expected to get the maximum deflection. So, we closely monitor the reading in the dial gauge. So, when it is directly above the point, that is the deflection that we note in the case of a washout procedure. On the other hand, in CGRA procedure, initially the load is directly above the point, at which we are trying to measure the deflection. So, the probe point will be here. So, the dial gauge reading corresponds to the position of the probe point corresponding to the deflected shape. When this load is removed away from the point, the pavement surface rebounds and the corresponding observation of the dial gauge is also made. So, what we get here is the rebound deflection. Indian Roads Congress 81 guidelines suggest that we have to adopt CGRA procedure. One can also adopt Washoe procedure also, but the criteria that we adopt has to be corresponding to the pavement evaluation technique also that we are adopting. If we are using CGRA procedure, the corresponding criteria has to be there in terms of the deflection that we measure. If it is a Washoe procedure, the deflection that we measure can be slightly different. So, the criteria also has to be different. So, the criteria that is available for us is on the basis of CGRA evaluation of pavements. The salient features of the beam are: the length of the beam from hinge to probe point is 2.44 meters. The length of the beam from hinge to dial is 1.22 meters. The distance from the hinge to the front legs is 0.25 meters. The distance from the hinge to the rear legs is 1.66 meters. The lateral spacing of the front legs, the spacing between the two front legs is about 0.33 meters. The loading that is to be applied is, we have to use a 5-ton truck. This is a standard truck. So, this is to be used to apply the load. What is important is, the rear axle of this truck has to weigh 8170 kg. If you recollect, this is the load that corresponds to standard axle load. 18,000 pounds or approximately equal to 80 kilonewton rear axle. This load has to be equally distributed over the two wheel sets. The standard truck that we are going to consider will have two dual wheel sets on either side. So, each one of these dual wheel sets will have to have 8170 by 2 wheel load approximately. The spacing between the tires, the dual wheel sets that we are going to use, so the clear spacing between these two tires will have to be 30 to 40 millimeters. Standard tires are to be used 10 by 20 12 ply. The tire pressure is again very important, 5.6 kg per centimeter square or 80 psi tire pressure has to be maintained. The other accessories beside the Benkelman beam that we need to have are a gauge for measuring the pressure, because we said the tire pressure is very important in the entire exercise. So, we have to keep monitoring the tire pressure that the tires have. If they deviate from 5.6, so we have to again adjust that. We also need to have a temperature measuring instruments, especially thermometers, which are capable of measuring temperatures in the range of 0 to 100 degrees centigrade, because we have to measure the pavement temperature, because the deflections in the case of bituminous surfacing, deflections get affected by the temperature of the pavement. So, these deflections have to be standardized to correspond to a standard temperature. So, we should know what is the temperature at the time of measuring the deflections. For that, we need to have thermometer. We also need to have a small mandrel, using which we can drill a hole into the pavement, and into the hole we can put some glycerol, and then we can put the thermometer to measure the temperature. So, we have to have all these elements to put a hole in the pavement temperature, small hole 4.5 centimeter deep, and put glycerol and then put the thermometer there. We should be able to measure the temperature of the pavement periodically. The procedure that has to be followed for measuring deflections using Benkelman beam is like this. First thing that we have to do is mark the point on the pavement surface. This has to be selected at a distance of 60 centimeters from the pavement edge as per the guidelines given in IRC 81. This is for single lane roads. So, if we have a single lane roads, we assume that the wheel path is approximately at a distance of 60 centimeters from the pavement edge. So, that is the path along which we are going to measure the deflections also. So, for single lane road, the points will be selected at a distance of 60 centimeters from the pavement edge. On the other hand, if we are using wider lanes, then the wheel path can be considered to be at a distance of about 90 centimeters from the pavement edge. For divided 4-lane highways, these are divided highways, 4 lanes, that means in each direction you have 2 lanes. So, in such cases, the wheel path can be considered to be at a distance of 1.5 meters from the pavement edge. So, that is the path along which we are going to measure the deflections. We have to place the outer dual wheel of the truck at the location. So, we have to center the outer dual wheel load. If this is the point at which we are going to measure the deflection, so the outer dual wheel load will have to be directly positioned about this point. The probe of the beam has to be inserted between the dual wheels. The probe will be directly resting on the selected point. The locking pin, this is a pin that was shown in the previous diagram. The locking pin will be removed so that the beam is free to rotate about the hinge. The support frame has to be leveled. This sketch here shows how to select the location of the points for measuring the deflections from the pavement edge, 0.6 meters, 0.9 meters, 1.5 meters for different types of facilities. The beam plunger has to be brought in contact with the stem of the dial gauge. Beam plunger is the arrangement that we have at the end of the beam, above which the plunger of the dial gauge will be resting. So, as the beam rotates in this direction, the plunger of the beam will be supporting the plunger of the dial gauge. Initial reading in the dial gauge will be noted. As you understand, load is already placed on the point, the probe of the beam is placed between the wheel loads. So, it is the initial deflected position and the corresponding position of the end of the beam we are noting using a dial gauge, because the pavement is already loaded, it has already taken a deflected shape. So, the probe point is on the deflected shape, the end point goes up. So, that is what we are observing using the dial gauge. Then we move the truck forward to a distance of 2.7 meters from the initial point. Then we observe what is known as initial intermediate reading in the dial gauge. So, as the wheel load moves away, the pavement rebounds, the end of the beam comes down, that position will be noted by the dial gauge reading. The truck will then be asked to move away by a further distance of 9 meters. So, starting from initial point of 0, the next position of the rear wheel load will be 2.7 meters. Next position will be after the wheel load is moved by a further distance of 9 meters. For this position, if there is any change in the dial gauge reading, we will note that as final dial gauge reading. So, there are 3 portions of the wheel loads: wheel load directly over the point, initial reading; wheel load placed at a distance of 2.7, intermediate reading; wheel load moved by a further distance of 9 meters, final reading in the dial gauge. These are the 3 readings that we are going to note down. We have to note down these dial gauge readings when either the rate of deformation or the rate of recovery is less than 0.025 millimeters. So, in its deformed condition, the rate of recovery has to be less than this. So, either the rate of deformation or rate of recovery has to be less than this. The photograph here shows the dual wheel set of the outer wheel with the probe point of the beam placed between, you may not be able to see it very clearly because it is under shadow. So, the probe point of the beam inserted between the two dual wheels, and these are the two front legs, other leg you cannot see, and this is the extension arrangement that we have. This is the support frame of the beam. While carrying out the deflection survey, we also have to measure the pavement temperature at least once every 1 hour by inserting the thermometer in the hole made in the bituminous surface and after filling the hole with glycerol. So, we have to measure the pavement temperature at 1 hour intervals. Tire pressure is also checked at 2 to 3 hours intervals, and if it is not 5.6 kg per centimeter square, we will have to adjust that. The three positions of the wheel load and corresponding the measurements that we take are represented here. The topmost arrangement, the topmost sketch that we have here, wheel load is directly placed over the point, and the probe point is at the bottom of the deflected ball. It is rotating about this hinge, and this is the position of the end of the beam for this loading position. So, we get the initial reading. When the load is moved to a distance of 2.7 meters, it rebounds. It may or may not fully rebound. So, it rebounds like this. So, the corresponding intermediate reading is noted. In the final position, the load is moved by further distance of 9 meters. In this position, it can be expected that the probe point fully rebounds, the pavement fully rebounds, and the corresponding dial gauge rating is noted as final rating. For a given stretch of maybe 1 kilometer, 2 kilometers, 10 kilometers, we will be making number of deflection measurements. It is not just at we measure this deflection at one point and then design the overlay on the base of that. We have to select a sample of points at which we are going to measure the deflections. On the base of all the deflections that we measure at all these points, we will work out a characteristic deflection which is representative of the entire pavement stretch under consideration, and we will use that characteristic deflection for design and assessing the condition of the pavement. At a given point, how we calculate the deflection is, that is how we calculate the rebound deflection is, we subtract the final reading from the intermediate reading, final dial reading from the intermediate dial reading. We also subtract the intermediate dial reading from the initial reading. If the difference between the final and intermediate dial readings is less than 0.025 millimeters, we normally should expect the difference should be negligible, because when the load is moved to a distance of 2.7, we should expect the pavement should have fully recovered, rebounded, and when the load is moved to a further 9 meters distance, there should not be any further rebound. That is the normal expectation. But it is quite possible that when the load is at 2.7, the pavement has not fully recovered, it is still influenced by the load placed at 2.7 meters distance, and when the load is fully further moved to a further 9 meter distance, that is a distance significantly large. So, that position should not have any influence on this point. So, that is a position when we consider the pavement has fully rebounded. If the difference between the intermediate reading and the final reading is more than 0.025 millimeters, we have to make some correction to the deflection that we get. If the difference is more than 0.025 millimeter, compute the rebound deflection as follows. Pavement rebound deflection is twice. This is when the intermediate and final readings differ by more than 0.025 millimeters. payment rebound deflection is given as twice final minus intermediate readings plus 2.91 times twice the difference between final and intermediate readings. This is when the intermediate and final readings differ from each other by more than 0.025 millimeters. If the difference is less, the payment rebound deflection is equal to twice final minus initial reading. As I said, we may have to be conducting Binklund beam evaluation survey for let us say 100 kilometers, and we cannot give one single value representing all the 100 kilometer stretch. What we have to do is, this complete stretch will have to be divided into smaller stretches having uniform characteristics. It can be 1 kilometer, 2 kilometer stretches. So, each 1, 2 or 3 kilometer stretch will have to have uniform characteristics, either in terms of the materials used, in terms of the traffic pattern, in terms of the subgrade condition, or especially in terms of the distress condition that we observe on the pavement surface. So, we have to identify, we have to initially conduct some visual examination and also carry out a few physical measurements to find out what is the present distress condition. On the basis of that, classify that into different types of pavement stretches. So, each pavement stretch will be handled differently. So, for selecting homogeneous sections, uniform sections, the pavements will have to be classified in terms of good, fair and poor sections, represented by pavement condition of good being no cracking, rutting less than 10 millimeter average, fair being no cracking or cracking confined to only a single crack in the wheel track, rutting in the range between 10 to 20 millimeters. It can also be classified as very poor if the extensive cracking is observed and rutting is more than 20 millimeters. Sections with cracking exceeding 20% shall be treated as failed. So, we can classify the road in terms of the cracking, rutting and select homogeneous sections on this basis. So, on the basis of surface condition survey, the total stretch can be divided into uniform sections. Length of each section is to be kept to a minimum of at least 1 kilometer, because we do not want to design overlays for every 200 meters. For each homogeneous or uniform section of road, a minimum of 10 points should be selected at equal distance in each lane of traffic. The points to be selected along outer wheel paths. Normally, we have to select these points along the outer wheel paths. The interval between points should not be normally less than 50 meters. On roads with more than one lane, the points on the adjacent lanes can be staggered. In case of extreme deflection values, the additional deflection measurements are to be made. For example, if the highest or lowest deflection differs from the mean by more than 1/3 of the mean, then extra deflection measurement should be made at 25 meters on either side of the pavement. We have to be careful about the extreme points, extreme deflections, then we have to make additional deflections if this criteria is satisfied. The measured deflections have to be corrected to correspond to a standard pavement temperatures. As I said, if you have a bitumen surfacing, the pavement deflections are going to be affected by the temperature of the pavement. At higher temperatures, the bitumen surface is going to be weak, then you get higher deflections. On the other hand, if you do the deflection survey in very cold temperature, the deflections will be low. So, this has to be normalized to a standard temperature. The measured deflections also have to be corrected to correspond to the worst condition, because we are going to consider the condition of the pavement, structural condition of the pavement when it is in worst condition. This worst condition would normally be attained soon after monsoon. The correction for standard temperature has to be done for a temperature of 35 degree centigrade. The guidelines are, the correction has to be 0.01 millimeter for each degree variation from 35 degree centigrade. For example, if the measured deflection or the deflections are measured at 38 degree centigrade pavement temperature, if it is 0.8 millimeters, then the corrected deflection will be, because the temperature is deflection is measured at higher temperature than 35 degree centigrade. So, we have measured higher deflections, they have to be reduced to correspond to 35 degree centigrade. So, the corrected deflection will be 0.8 minus 3 into 0.01, that is a correction for each degree of difference in temperature. So, the corrected deflection will be 0.8 minus 3 into 0.01, that is 0.77 millimeters. Similarly, correction for seasonal variation also can be done. This has to be done for the weakest condition, which will be soon after monsoon. Deflection will vary with variation in subgrade strength, which is affected by the variation in moisture content with season, and also it is a function of the type of soil that is there. For correction of seasonal variation, field moisture content of the subgrade soil sample has to be determined during the deflection survey. While you are conducting deflection survey, we have to collect soil samples from the subgrade and determine the moisture condition. We also have to find out the type of soil. So, on the basis of the type of soil, on the basis of the field moisture content, moisture correction factors or seasonal correction factors are given in the guidelines. So, correction factors are available for different types of subgrade soils, different rainfall conditions, and for different field moisture contents. Three categories of soils are considered: clay with low plasticity, pH less than 15, clay with high plasticity, pH greater than 15, and sandy gravelly soils. The correction for seasonal variation can be obtained from the charts that are given in the guidelines. For a given moisture content, this is the field moisture content that is measured on the basis of the soil sample that is collected, and for a given soil type and for a given rainfall category. Rainfall categories are, two categories are considered: less than 1300 millimeter annual rainfall, greater than 1300 millimeter annual rainfall. So, for either of these two categories and for different types of soils, a series of charts are available. So, for a given soil type, for a given rainfall category, and for the measured field moisture content, the moisture correction factor can be obtained. On the basis of number of deflection that we measure in a given stretch, representative rebound deflection value for the length of the uniform stretch can be selected. This is known as characteristic deflection, which represents the overall condition of the pavement. This is obtained, DC is obtained as mean of all the measured deflections plus some factor multiplied by the standard deviation of all the measured deflections. For major arterial roads like national highways and state highways, the characteristic deflection can be obtained as mean plus 2 times standard deviation. For all other roads, it can be mean plus 1 standard deviation. For designing overlays, the following steps are to be followed. First thing that we have to do is select design period. Next, we have to project the commercial traffic that is going to be there during the design period. If you select design period of 10 years, so over the next 10 years, after the pavement is constructed, for a further period of 10 years, how many standard axle load repetitions this pavement is expected to serve. So, we have to have that number. We have to estimate the cumulative standard axle load repetitions for the design period. We have to select characteristic rebound deflection for the existing pavement on the basis of rebound deflection survey conducted using Benkelman beam. That is what we have discussed so far. How to select a characteristic deflection, how to conduct the survey, how to get the deflections, sample of deflections, then on the basis of that, how to calculate the characteristic deflection. So, that is representative of the given stretch. Traffic projection can be made in the following manner. Traffic A, which is commercial vehicles per day in the era of completion of construction, can be obtained from the traffic count that we have made some time back, let us say. So, P is the commercial vehicles per day at last count. A is the annual rate of increase of commercial vehicles. If we have some information about, more authentic information about this, we will use that value. Otherwise, IRC suggests that you can use a value of 7.5%. N is the number of years between the last count and the era of construction of overlay, completion of overlay construction, because we might have made this, obtained the value of P 2 years back, and maybe the overlay is going to be constructed after another 3 years. So, the time that has elapsed between the last count and the completion of construction of the overlay could be 5 years. So, the traffic intensity would vary by that time. So, we are going to estimate A value on the basis of the P that we have obtained about, let us say, 5 years back using this expression. From the value of A that we estimated, N, which is the cumulative number of standard axles to be catered by the payment during the design period, N, this is in terms of cumulative standard axles, is given as N equal to 365 A into 1 plus R to the power x minus 1 into F divided by R. R is the annual rate of growth of commercial vehicles. Authentic projections have to be made on the basis of various data that one has to collect for projecting this. If it is not available, a value of 7.5% can be taken. X is the design life in years, normally taken as 10 for major roads and 5 for less important roads. F is the vehicle damage factor. The value of A has to be adjusted for lane distribution. For single lane having a width of about 3.75 meter, the total two-way commercial traffic multiplied by 2 has to be taken. Though it does not appear to be very logical, but this is the guideline that IRC 81 has. If you recollect the guidelines given in IRC 37, which is for design of flexible pavement, which has been revised subsequent to 1997, there the lateral distribution factor taken for single lane roads is 1, that is, we are going to take 100% of the total two-way traffic. However, in the case of IRC 81, this provision of multiplying the total two-way traffic by 2 still remains. For 2-lane single carriageway having two-way traffic, we are going to take 75% of the total two-way traffic. For 4-lane single carriageway, 40% of total two-way commercial traffic. We have 4 lanes total, but it is single carriageway. There is no division between the 2 lanes in the 2 directions. It is a single carriageway, it is not divided facility. In that case, we are going to take 40% of the total two-way traffic. We are interested in only commercial traffic only. Similarly, if you have dual carriageway, 75% of the commercial traffic in each direction for dual 2-lane carriageway is going to be considered. For each additional lane, reduce the distribution factor by 20%. And for estimating the traffic, we also need vehicle damage factors. We know that this has to be obtained from axle load survey, but if axle load survey data is not available, indicative VDS values are for different commercial traffic intensities 0 to 150 initial traffic. We can select a value of 1.5 for rolling and plain terrain, 0.5 for hilly terrain. For 150 to 1500 commercial vehicles per day, 3.5 for rolling and plain terrain, 1.5 for hilly terrain. Similarly, if the commercial traffic intensity is more than 1500, 4.5 for rolling and plain terrain, 2.5 for hilly terrain. So, this is how we can select the vehicle damage factors. So, thus we can estimate N, which is the cumulative standard axle load repetitions that the payment has to cater to. IRC 81 has typical design charts using which we can select the overlay thickness. Characteristic deflection, depending upon the importance of the facility, mean plus 2 standard deviation or mean plus 1 standard deviation, that value has to be selected. On the basis of the characteristic deflection and on the basis of design traffic, 20 million standard axles, 10 million standard axles. So, after we estimated that also, we get the thickness of the overlay to be provided in terms of bituminous macadam material in millimeters. So, this is quite simple. What we have to obtain is characteristic deflection from Bengaluru beam survey conducted, corrected for temperature, corrected for season. So, we select either mean plus 2 sigma or mean plus 1 sigma depending on the importance of the facility. Obviously, if you select mean plus 2 sigma, we are using the same chart. So, we get higher bituminous macadam thickness. If you use mean plus sigma for lesser important roads, you get lesser characteristic deflection. So, for this naturally you will get lesser overlay thickness. So, we have the overlay thickness in terms of bituminous macadam. We may not be using bituminous macadam, obviously bituminous macadam cannot be used for surface. So, this has to be replaced by the total BM requirement has to be provided in terms of DBM, also it can be in BM, DBM, BC or other types of bituminous layers. So, using the conversion factors that are given here, we can convert the total requirement of BM into different component layers. For example, BM can be converted into other materials using equivalency factors, that is 1 BM is equal to 1.5 WBM or wet mix macadam or built up spray grout layer. If we are going to replace some requirement of BM in terms of WBM, WMM or built up spray grout. Alternately, if you are trying to replace BM in terms of DBM, AC or BC bituminous concrete or semi-dense concrete, equivalency is 1 BM is equal to 0.7 DBM, AC or STC. Minimum thickness of overlay that has to be provided irrespective of all the calculation that we get is 50 millimeters BM with an additional surfacing course of 50 dBm or 40 BC. Let us take an example. The data that is available is subgrade is of sandy soil. Moisture content that was measured during the deflection survey was 8%. The pavement temperature was observed to be 35 degrees centigrade. We remember 35 is the standard temperature to which we have to adjust all the pavement measured deflections. So, incidentally the temperature itself is 35 degrees centigrade. So, we will not be making any correction for pavement temperature. The area has an annual rainfall less than 1300 millimeters. The existing traffic is 5000 commercial vehicles per day. Design period has to be 10 years. Traffic growth rate can be assumed to be or is given as 7%. Vehicle damage factor on the basis of accelerated survey is found to be 4.5. We have to design an overlay for this pavement which is a national highway. This is a typical deflection data that was measured. So, initial deflection, intermediate deflection, and then this is how we calculate the mean and standard deflection. This is the mean value, this is standard deviation value. From this is how we are getting characteristic deflection as mean plus 2 sigma. We are not making a correction for temperature, but we are making correction for moisture. This is the correction factor that is obtained. Traffic is estimated in this fashion. A is given as 5000, lane distribution factor of 0.75, this is a 2-lane two-way highway. Vehicle damage factor of 4.5, growth rate of 0.07. So, the traffic that the pavement has to cater to is 8.85 million standard axles. The characteristic deflection works out to be 1.06. This corrected for temperature, there is no correction, and this corrected for moisture or season is 1.03 is the correction factor. So, the corrected deflection is 1.09. So, for 95 million standard axles and 1.09 characteristic deflection, using the thickness charts given in IRC, the total overlay thickness works out to be 160 millimeters of bituminous macadam. So, I split this into 50 millimeter of BC and 70 millimeter of BM. So, we can verify whether this is correct or not. BM is bituminous macadam and BC is bituminous concrete. To summarize, in this lesson we have discussed about the basis for IRC 81/1997 guidelines for design of overlays. We also discussed the detailed procedure for conducting Bengal beam deflection survey. We also discussed about the corrections to be made to the deflections that are measured in terms of temperature correction, in terms of seasonal correction. We also discussed how to select overlay thickness on the basis of Bengal beam deflection study and also on the basis of other information that we collect during the survey. Let us take the questions, let us take the answers to the questions that we asked from lesson 5.1. lesson 5.1 was on evaluation of payments. What are RTR-MMS? RTR-MMS are response type roughness measuring machines. These are equipment that give an index of roughness of the payment, and this is the index that is sensitive to the road user's perspective. Compare Merlin with fifth wheel bump integrator. Merlin and fifth wheel bump integrator are entirely two different equipment. Fifth wheel bump integrator is a response type equipment which responds to the, which has got a suspension system, and what we measure there is the cumulative stroke of the suspension system. In the case of Merlin, what we measure is how the distribution, how the variation of the midpoint of a straight line drawn between 2 points on the payment surface, how it varies, its variation is distributed. So, that distribution gives us an index of the roughness of the payment. So, while the roughness parameter that we obtain using a fifth wheel bump integrator can vary over time, can be different for different equipment, Merlin is more or less standard. So, that is why it is normally used to calibrate response type equipments. Why is it necessary to calibrate RTR-MMS? Response type equipment, as I just mentioned, their response will be varying with time, and similarly for a given road, if you use different types of RTR-MMS, we get different roughness values. So, that is why these have to be standardized to correspond to a standard index. So, that is why we have to calibrate these RTR-MMS. What is a golden car? Golden car is a hypothetical 1/4 of an equipment which is used in the simulation of its response to a given profile to calculate international roughness index. So, the parameters of this, the body of the mass, body of the axle, suspension system and the stiffness of the tire, they are so selected, fine tuned, so that the IRA value that is computed correlates well with the response type measurements. So, the finely tuned parameters and the corresponding system is called as golden car. In fact, this is a quarter car. Why is FWD evaluation better than Bengal beam evaluation? In FWD evaluation, we get information about the deflection bowl of the payment, whereas in the case of Bengal beam, we get only one deflection, which is the maximum deflection, whereas in FWD we get number of deflections. So, as a result, we get more information about the payment compared to the information that we get from Bengal beam evaluation. So, FWD is always better than BB evaluation. We will have a few questions from this lesson. Why do we multiply the deflection obtained from the dial gauge readings by 2? This we have to do because the beam is hinged about a location which has got 2:1 ratio in terms of length. So, that is the reason why we measure the deflections obtained from the dial gauge by 2. What are the corrections to be applied to the surface deflections measured using Bengal beam? We have to apply temperature correction so that it corresponds to a standard temperature of 35 degrees centigrade. We also have to apply seasonal correction on the basis of the moisture content that we obtain, so that the deflection corresponds to the worst condition. What is the load applied to the pavement for measuring surface deflections in the Bengal beam procedure? The load applied is through a truck. The rear axle has to be 8170 equally distributed on the both the dual wheel sets. The tire pressure has to be 0.56 MPa. What are the parameters on which the overlay thickness as per IRC 81/1997 is based? We can select the overlay thickness using characteristic deflection and also on the basis of the cumulative standard axle load repetitions. Thank you.